Welcome back to The Explainer. Today, we're diving straight into a totally invisible, yet absolutely fascinating world, the back end of machine vision. We interact with this tech literally every single day, right? Yet, how a computer actually processes the world around it is kind of a complete mystery to most of us. Well, not anymore. Let's jump right in. I mean, just think about this for a second. A robot on a super busy factory floor can scan a fast-moving conveyor belt and spot a microscopic scratch on a tiny component in zero point 0.1 seconds. Or consider a self-driving car navigating a chaotic city intersection. It can perfectly identify a pedestrian stepping off a curb in the pouring rain at night. And both of those examples, they're using the exact same underlying technology. But that brings us to the real million-dollar question for today's explainer. How do they do it without eyes? How does a machine, which is essentially just, silicon and wire, actually see the physical world? The stakes here are massive, impacting everything from the safety of our daily commutes to the speed of the global supply chain. To figure this out, we're going to follow an image down a sort of digital assembly line. First, we'll cover seeing beyond human eyes, then building the digital mosaic, finding edges and shapes, learning like a toddler, where is the cat, and finally, the new vision revolution. Okay, step 1, seeing beyond human eyes, the blank canvas. So because machines obviously don't have biological retinas, we need to start with a clear definition. Machine vision is the use of cameras, sensors, and algorithms to give machines the ability to interpret visual information from the world. Basically, this isn't just taking a photograph, it's the technology of giving computers the ability to actually comprehend what that photograph contains. And it's the fundamental tech quietly reshaping almost every major industry right now. When we look at a furry little cat, we just see, well, a cat. But the machine? It sees a giant digital mosaic. It literally just sees a massive spreadsheet. Every single pixel in an image is represented by numbers, specifically red, green, and blue, or RGB values. It doesn't see fur or whiskers. It sees a grid of millions of numbers ranging from 0 to 255. Moving right along to step 2, building the digital mosaic. Capture and pre-process. So how does it make any sense of that crazy grid of numbers? For a machine to actually see, it runs through a really fast 3-step core pipeline. Capture the pixels, pre-process the image, and then extract the features. It's a highly organized, completely automated assembly line. And what's wild about the capture phase is that because machines don't rely on squishy human eyes, they aren't limited by human biology. They can capture data that is entirely invisible to us. By using infrared cameras to see heat, depth sensors to instantly calculate distance, and multispectral cameras to analyze chemical makeup, machines essentially have superpowers right out of the gate. But before the computer can actually analyze all that captured data, it's got to clean it up. Think of pre-processing a lot like wiping a dirty, smudged window so you can finally see outside clearly. The system normalizes the lighting, reduces digital noise, and bumps up the contrast. If you've ever put on a pair of glasses and suddenly a blurry world just snapped into sharp focus, yeah, that is exactly what pre-processing does for an algorithm. It guarantees accuracy. Which brings us to section 3, finding edges and shapes, finding the puzzle pieces. Once that window is clean, imagine you're putting together a 1,000-piece jigsaw puzzle. What's the very first thing you do? You look for the corner pieces, right? Then the flat edges. Well, machine vision works the exact same way. Feature extraction algorithms scan that giant grid of numbers, looking for sudden changes in color or brightness. These sudden changes indicate edges, corners, shapes, and textures. These 4 elements are the fundamental building blocks of object recognition. Before it even knows it's looking at a stop sign, it just knows, hey, I found a red octagon with sharp white edges. Next up, section 4, learning like a toddler, flashcards for AI. All right, so the machine has its puzzle pieces, but how does it know what it's actually looking at? Enter convolutional neural networks, or CNNs. This is the heavy lifter. CNNs are deep learning architectures that learn to recognize patterns by training on millions of labeled examples. Imagine sitting down with a toddler and showing them a million different flashcards of a bicycle, from every angle and every lighting condition, until they just intuitively understand what makes a bicycle. That's what a CNN does. And it is the exact breakthrough that completely transformed modern machine vision. But here is the catch, summed up perfectly. A vision model is only as good as its training data. If you only show that toddler flashcards of red bicycles, they might not recognize a blue one. If you feed a machine vision system flawed, biased, or incomplete datasets, you are absolutely going to get an inaccurate and unreliable system. In the world of AI, junk in equals junk out. Section 5. Where is the cat? The Where's Waldo problem. Knowing what an object looks like is one thing, but finding it out in the wild, totally different ballgame. Notice the massive distinction here. Classification is simply the computer looking at an image and saying, yep, this image contains a cat. But detection, that is way harder. Detection says, there is a cat, and it is located exactly at coordinates X and Y. Think of it like a Where's Waldo book. Classification is just knowing Waldo is somewhere on the page. Detection is actually pointing your finger directly at him in the middle of a massive crowd. And the holy grail for pointing out Waldo instantly is an architecture called YOLO, which stands for You Only Look Once. Now, older systems used to scan an image chunk by chunk, kind of like reading a page word by word. It was painfully slow. But YOLO? It processes the entire image in one single forward pass. It looks at the whole page in one glance. This is a total game changer because it enables real-time video speed object detection. Finally, Section 6, the new vision revolution, real-world stakes and optical illusions. Because this tech isn't just theory anymore. It is everywhere. Just look at how rapidly it's deploying across all these industries. In e-commerce, Amazon robots are using machine vision to pick specific products out of totally chaotic bins. In healthcare, radiology AI is spotting tumors and x-rays that human eyes could easily miss. In agriculture, automated drones are flying over massive fields, identifying disease crops pixel by pixel. And the technology just keeps getting deeper and more nuanced. We now have semantic segmentation, where the machine categorizes every single pixel on the screen like a highly complex paint by numbers. That's essential for self-driving cars to actually understand a busy street scene. We have 3D vision using LiDAR, acting like digital echolocation to give robots real depth perception so they don't, constantly crash into walls. And we have optical character recognition, or OCR, which is the exact magic behind Google Translate reading a foreign menu through your phone's camera, or a scanner reading your passport at airport security. Hundreds, as in hundreds of frames per second. That's how incredibly fast modern vision chips, like NVIDIA's Jetson, can process data directly on the device. They don't have time to send data all the way up to the cloud and wait for an answer. For a self-driving car or a surgical robot, the machine needs to make highly complex, literally life-or-death visual decisions in mere milliseconds, completely on its own. But, and this is a huge but, it is not flawless. Because machines ultimately see numbers, not concepts, they're vulnerable to what we call adversarial attacks. Think of this as an optical illusion specifically designed for a computer. By making tiny, totally imperceptible changes to an image's pixels, changes you and I couldn't even see, hackers can trick a vision model into completely misclassifying an object. They could literally make a self-driving car think a stop sign is a 65-mile-per-hour speed limit sign. It's a major, major safety concern as we rely more and more on these systems. Which leaves us with this final, incredibly important question to ponder. How much should we trust a world washed by machines that see so entirely differently than we do? I mean, they're faster, they can see invisible light, and they literally never get tired. But they also don't possess human context or common sense. Machines are learning to see the world, and that changes absolutely everything. Thank you so much for joining me on this explainer. If you found this breakdown helpful and want to understand the invisible tech shaping our future, be sure to subscribe. Catch you next time.